Hi everyone. In this video, I'm going to show you how three-phase rectifiers work. A little bit of prerequisite for this video would be an earlier video I made about how to chart sine waves in Excel, and another one about how single-phase rectifiers work. So what I've currently got charted on the graph here, what I've currently got graphed on the chart here in Excel is a three-phase AC waveform where all three phases, A, B, and C, are all separated from each other by 120 degrees. So they're evenly spaced across the period for which they oscillate. There are two types of three-phase rectifiers that I'm going to show here. This top one is very similar to the three-phase rectifier or the single-phase rectifier I discussed a few videos back. And instead of having just a single phase go through a diode out to the load and back to the source, we're taking the other two phases and connecting them to diodes forward biased so that we get the highest value basically out of any of these three incoming phases. And what that's going to do with reference to neutral is give us a voltage that just follows the highest currently present sine wave in this graph we see now with reference to neutral. So I'm going to go ahead and turn on that sine wave or that output, and that's this blue wave here. See how it just rides the top of each of the sine waves for phases A, B, and C. We still have a fairly choppy peak up here to where we'd have quite a bit of ripple on our output. And one thing we can do to help smooth that is to use a three-phase rectifier like we see down here in the bottom. And this is similar to the single-phase full-wave bridge rectifier that I discussed before as well. And this one works a little better because instead of referencing neutral, we're going to reference our high point output to the lowest point output of any of the three sine waves. So what I'll do now is I'll turn off, I can leave that one on, I will turn on what the output of that looks like. It's much higher, as you would expect. That's going to be a square root of 3 increase multiplying factor over the peak value of any of the sine waves you see here. That's just a natural property of three-phase systems. So if we have 1 here, multiply it by the square root of 3, and that's going to tell you our peak value up here. And the reason this is so much higher is we are referencing, one of the reasons it's so much higher is we are referencing the high point of the sine wave not to 0 volts, but to the lowest point of any of the other sine waves. So we really have to shift all of this point up to 0, which shifts this point up. Another thing you'll notice is that our top rectifier over here, our output waveform is in phase with each of our other sine waves. If you look at our top waveform up here, we're shifted by 30 degrees. And that's because we are referencing another sine wave instead of neutral. So we get a lot more ripples up here, but they're also smaller in magnitude, so that'll give us a cleaner output. And this is something that's very typically used on power electronics front ends, such as variable frequency drives or VFDs. And it will take the three-phase incoming power, that's a low end or regular industry VFD that doesn't have any regeneration capabilities or shared common buses, anything like that. This is just AC in, and power is only able to flow to the load. So they will do this rectification on the front end and get this all completely fully rectified three-phase output. They'll add some capacitors to smooth that up, turn it into DC, and then they'll have some IGBTs, some power transistors on the output that will allow us to turn that on at high frequencies and rebuild an RMS wave that allows us to control the speed and torque of a motor. So a little more illustration here would be showing you where the measurement up here in this top waveform is coming from. So as I click along here on my scroll bar, you'll see this black line down here is showing you that from that point to this point, that's actually our peak or our valley in between each of our fully rectified sine wave cycles up here. You'll find the highest point is about halfway through this upward incline on the single or on the three-phase rectified with reference to neutral, and the point directly below. So if I go to about right there, that's about our biggest voltage difference or difference in potential. And then it gets small again, large again, small, large, all the way across these three sine waves. And there's a lot we can do with that, and I'll discuss that in some future videos about how the transistors work and maybe some removal of noise and harmonics from the bus and the output. And one of my next videos will also be about reconstructing different shapes of waves using sine waves and harmonics thereof. So if you have any questions about this video, feel free to leave a comment and go ahead and like and subscribe so I can continue making these videos for you. Thanks a lot.